colleagues, students, ladies and gentlemen, good morning, good afternoon, and good evening. It gives me great pleasure to introduce our keynote speaker today, Professor Linshan Li. Limited number of distinct monosyllables, tones, etc., as well as the extremely limited resources. He then focused his work on speech information retrieval, proposing a whole set of approaches making retrieval performance less dependent on ASR accuracy and improving retrieval efficiency by better user content interaction. This part of the work applies equally to all different languages and was described as the stepping stones towards a spoken version of Google when Nature selected him in 2018 as one of the 10 Science Stars of East Asia in a special issue on scientific research in East Asia. I must also mention that Professor Li has dedicated his services to the ISCA board for 8 years between 2001 and 2009, during which time he established the ISCA Distinguished Lecturer and Geographical Outreach programs. He is also a founding leader who established the Special Interest Group in Chinese Spoken Language Processing under ISCA, bringing together the researchers across Greater China and other regions. Please join me in a very warm welcome to Professor Li.
Helen, thank you very much for your very nice words. And hello to everyone. Good morning, good afternoon, good evening for everyone globally. It's my great honor to give the talk here, and this is really my first experience to give a talk in a virtual conference. Thank you very much for this opportunity. So please go ahead to play the video.
Hello, good morning, good afternoon, good evening to everyone globally. I hope all of us can be kept safe and healthy. Although I'm not able to talk to you in person right now, I do look forward to doing that very soon in the future. Today is my great pleasure to give this talk. The title of the talk is Doing Something We Never Could with Spoken Language Technologies. My name is Linshan Li from National Taiwan University. Let me start with explaining what I'm going to say and why. As we know, some research effort tries to do something better, while some tries to do something we never could. Good examples for the former includes having aircrafts fly faster, having images look more beautiful. Good examples for the latter includes developing the internet to connect everyone over the world and selecting information from internet with Google. The former is always very good, while the latter is usually challenging. This talk is about the latter one. A major problem for the latter one is that very often those we could never do before are very far from realization. We usually have to wait for long for the right industry to appear at the right time to realize it. And when that happened, very often new generations of technologies were used, very different from the earlier solutions found in research. However, this type of work are usually very interesting and exciting, and that's why I'm going to talk about this. Below, I'll give you 3 examples of this kind of work. They are, the first one, teaching machines to listen to Mandarin Chinese. The second is works toward a spoken version of Google. And the third is unsupervised ASR, or phony recognition. So let me start with the first example, teaching machines to listen to Mandarin Chinese. I believe we human beings start to talk to machines in writing, that is, typewriting. Some of you may remember the English typewriter. This is the machine, and here is a keyboard, very similar to the keyboard we have right now with our notebooks. When you push these buttons here, the letters will print it here. This is for English, but what happened for Chinese typewriters? Well, you have to know that Chinese language is not alphabetic, and every Chinese character is a square graph like this. And actually, there are many thousands of such characters. So what can we do with Chinese typewriter? It is something like this. That's a real machine. You need to have a very big keyboard. There are thousands of characters on it, like this one. And that's not enough. You need another set of many characters there to use. This is very troublesome. This is the time when I returned and started to teach in Taiwan University, the year 1980. I call it the age of Chinese typewriters. Because type Chinese characters are so troublesome, many people are trying to represent Chinese characters with some kind of code sequences like this. And at that time, a concept came to my mind. That is, can we have a voice-driven typewriter for Chinese? The basic idea is that every Chinese character is actually produced as a monosyllable, and the total number of distinct monosyllables is about 1,300, which is limited and about manageable. So we should be able to produce monosyllable by monosyllable and type character by character. That's something we could never do before. However, with some initial studies, I found that this means we need to teach machines to listen to Mandarin. That was too difficult in 1980, even difficult for English. So I changed my mind. I decided to do another work, that is to teach machines to speak Mandarin first. Today, we understand this is simply speech synthesis, or TTS. The first problem I need to solve is the computation resource. At that time, all I had is a microprocessor called BitSlice, which is very weak. And I thought the first requirement I need to meet is a real-time requirement, that is to produce 1 second of voice data within 1 second of time from linear predictive coding LPC coefficients, which were the most efficient speech parameters at that time. In order to do that, I decided to do hardware-assisted voice synthesizer first. So this is the hardware, and the microprocessor is here, but there are a lot of hardware to support it. This was completed in 1981 and used in the next several years. With that, I started to calculate and store the LPC coefficients and the tone patterns for all Mandarin monosyllables. And then I try to concatenate isolate monosyllables into utterance directly. And you may know that this never works, because any utterances produced in this way are totally just not intelligible. Even native speakers cannot recognize these sentences. I didn't understand why, but was stuck for long until I met a linguist and learned from the linguist that there is something called prosody, which includes pitch, energy, duration, and so on. And even the prosody of the same monosyllable is different in different contexts in continuous speech. This is called context dependency. But nobody knew at that time what this dependency is. Oh, I see. Then I think we should learn this from data. So I decided to make sentences and record voices and analyze the prosody. With great effort, we eventually came up with a set of prosody rules for every monosyllable in continuous speech based on the context. With these rules put back to the machine I just mentioned, we found that the synthesized voice is still very poor. However, they become intelligible. We can recognize what was said. Wow, that's wonderful. We are very excited. And today we realize what we did is simply data science in early years, except we did everything by hand, using only tiny amount of data produced by hand. The lesson I learned here is that linguistics are really important for engineers. You may wonder who that linguist is. Well, she is Professor Chu Yu-Chen. Many of you know. That was the year 1984, and this is the complete process rules we did for 1984. Let me give you one example of the Tong-Sandy rule here. Suppose we are going to synthesize a sentence of this. The problem here is that all these characters is pronounced in tone 3. Some of you may know there is a concatenation rule for tone 3. That is, if two monosyllables, both of tone 3, are connected, then the first tone 3 should be pronounced as tone 2. 3-3 becomes 2-3. But nobody knows what happens if this becomes so many tone 3. After great effort, we eventually found the solution. That is, we need to parse this sentence into a parsing tree. Then here are many syntactic boundaries, and this 3-3 to 2-3 rule actually has this principle that this rule applies across certain syntactic boundaries, but not for others. With this principle applied, we realized all these tone 3 here actually should be pronounced as some of them in tone 2 and so on. And this becomes 我有好几把小雨伞. This is the exact way that all native speakers will say this sentence. Here is very brief recording we did in 1984 for you to listen to, so you can understand what kind of voice was produced at that time.
早在69年初，我就想尝试进行语音处理的研究。当时我连信号处理的观念都很缺乏，对语音信号更是毫无经验。我于是由教科书开始读习，并带2位大四的学生开始做实验。当时没有经费，没有电脑，没有实验室，好。
With that, we understand speech processing really depends on sentence structure. So I believe we should start to study Chinese sentence grammar and parser. By 1986, we did a lot of work on that area, and one example is shown here. That is I called empty category, which means in a sentence like this one, actually there are many elements missing here. But if you put this element back, they will be very helpful to construct a parsing tree. Today, we realize this is just natural language processing in early years. With all this, by 1986, I thought I'm ready to do Mandarin speech recognition. So I started in 1986, and my initial setting was very large vocabulary, unlimited text, but just isolated monosyllable input, as we just mentioned, because every character is pronounced as a monosyllable, but total number of distinct monosyllables is limited. In this way, this is exactly a voice-driven typewriter. That was my goal. Because we are just to recognize one monosyllable, so I decompose this monosyllable into small subproblems. For example, the recognition of the consonants, vowels, and tones, and so on. And after this monosyllable is recognized, I need another problem to identify what the target character is in the user's mind among many homonym characters sharing the same monosyllable. When all these subproblems were done, I then realized there is still a very big problem, which is system integration. Because at that time, the software was very weak, and every Sub-problem mentioned above were handled with different hardware. So I thought we just put all the hardware together. Here is one example of circuit diagram we did in 1989. And by 1989, we did completed a system like this. However, this system never worked because the hardware and software are so complicated, we were not able to debug it. By 1990, we started to be able to do chips. So I decided we should do chips. By 1992, we accomplished 2 chips, one for LPC analysis or feature extraction, the other for bit-to-bit decoding. However, this is still very far from a complete system. Very fortunately, in 1990, a new computer appears in the Western world, which is called transputer, which is a parallel computer. You can collect many CPUs to work together in parallel. So I decided to use all my funds in my lab to purchase one transputer, including 10 CPUs operating in parallel, and redid everything on software in parallel. By 1992, it worked. Wow, it's wonderful. We are very excited, and I decided that I should give it a name. So I go through the classic Chinese literature and found this word, 金声玉振, which means the most beautiful song in the world. It's a song produced by using a piece of gold to knock a piece of jade, or 金玉之声. So I decided to call this machine 金声一号, or Golden Mandarin 1. It is isolate monosyllable input, and it takes several seconds to recognize a syllable. The lesson I learned here is software is really much more powerful than hardware, because before that, I always used hardware to support software. Here is a short video to show you how that machine looks. Of course, this person is myself.
This is a Mandarin speech recognition system with very large vocabulary. The primary application of this machine is in the input of Chinese characters into computers. During the operation, the voice are first received by the microphone and then sent to the amplifier and filter. After the AD conversion, the voice data are transferred to the PCAT and then primarily processed by the transputer system, in which 10 processors are operating in parallel.
These are the characters. These are phonetic symbols.
要 付 责 任
The next major breakthrough will be 1995, the Golden Mandarin 3. In that case, we can take continuous speech input. Because of the limitation of computation resources, we implement 2 versions, A and B, respectively on PC and workstations for short utterances and long utterances. Here is a very short video to show the PC version, version A.
This is Golden Mandarin 3 dictation machine version A, implemented on a 486 personal computer. It accepts continuous Mandarin speech in form of arbitrarily divided prosodic segments for input of Chinese characters.
电脑科技的进步。
your good. Yes.
改变了人。
Okay, this is the end of the first story. And let me give you some mini remarks here. Today, we know it's very easy for everyone to type Chinese characters into his cell phone. In other words, a dream many years ago was realized by the right industry at the right time with new generations of technologies. The lesson I learned here is that there's no worry about realization during research because someone will solve the problem in the future. Now let's talk about the second example, works towards a spoken version of Google. Around year 2000, many colleagues work on a problem called spoken content retrieval with a standard task called spoken term detection. That is to detect if a target term was spoken in any of the utterances in an audio data set. For example, suppose the target term is COVID-19. We hope the machine can tell us that in this utterances, the target term COVID-19 was spoken here, and so on with these scores. The basic approach for this spoken content retrieval problem is that we can apply directly a recognition engine in those years, including acoustic models, language models, onto this spoken content and transform it into some transcriptions. And then we apply a text-based search engine on top of these transcriptions. And therefore, for a user query, we get some results. The problem of this is that the recognition engine always produces errors, and this recognition errors cause serious problem to the retrieval results. Many people propose some good approaches, for example, use of lattices rather than one best output, and use of subunits and so on. At that time, we noticed that the ASR error problem really came from we are cascading two stages. In other words, we use the first stage of recognition to transform the content into lattices, and then we apply the second stage of retrieval on top of these lattices. So this is cascading, and therefore the output performance is definitely limited by the recognition accuracy here. This is why in year 2010, we proposed to consider recognition and retrieval process as a whole to optimize the overall retrieval performance by re-estimating the acoustic models. Today, we realize this concept is simply end-to-end spoken content retrieval in early years, because in early years, we didn't know ASR can be performed end-to-end, and we didn't know the retrieval can be integrated with end-to-end ASR. And that's why we did this way. We did a lot of work along this line, but at the same time, we asked the question, what can we do with spoken content retrieval? We noted that Google reads all text over the internet, and that's why it can find any text over the internet for the user. However, all rows of text can be realized by voice. So, as long as a machine can listen to all voice over the internet, machines, of course, can find any utterances over the internet for the user. And this is actually a spoken version of Google. But what can we do with a spoken version of Google? We noted that multimedia content is increasing exponentially over the internet. For example, YouTube. Hundreds of hours of videos uploaded per minute during the peak hours. There are thousands of online courses over the internet. We may say the best archive of global human knowledge is here. However, usually the desired information are deeply buried under huge quantities of unrelated information. Nobody can go through so much multimedia information, but machines can. So machines may be able to listen to and understand the entire multimedia knowledge over the internet. And then they may extract desired information for each individual user. What does that mean? Well, let me give you a target application example in our mind, which I call personalized educational environment. We hope for every individual user. For example, a user was planning to attend Interspeech 2019 in Austria, and he learns that Austria is the homeland of a very famous musician called Wolfgang Amadeus Mozart. So he asked machine, he wished to learn about this musician, but he can spend about 3 hours to learn. Can the machine go to the internet, find relevant information, and come back saying that this is the 3-hour personalized course for you, and I'll be your personalized teaching assistant. Feel free to ask me when you have questions. In order to do this, we need to be able to understand, summarize, and question answer for spoken content. This is something we could never do even today. And semantic analysis for spoken content is necessary for this kind of tasks. Because in early years, we didn't have BERT and we didn't know about word embedding. So in order to perform semantic analysis, we rely on the very useful topic analysis techniques, such as probabilistic latent semantic analysis, or PLSA, as well as the latent heuristic allocation, or LDA. Because with these techniques, we were able to extract better key terms, because the key terms are usually focused on smaller number of topics, like this. And also, we can do better summarization, because we can select most representative utterances, but avoiding redundancy. On the other hand, we note that it must be important to construct semantic structures for the spoken content, which I call it as semantic structuring. One example we propose is to cluster or categorize the spoken content by topics and organize them in a two-dimensional tree structure. In this way, every cluster or every category is labeled by a set of key terms, which define the topic and is located on a map. And the categories or clusters nearby on the map are more related semantically, and a cluster or category can be expanded into the next layer as another map. So this is a two-dimensional tree structure. Here is one example of the broadcast news browser we developed in year 2006. Here are the 9 clusters of broadcast news. Every one is labeled by a set of key terms. And this is a map of this layer, and it is expanded from this cluster on the upper layer, and so on. On the other hand, we consider online courses, because in courses, the knowledge transfer is usually sequential, lecture by lecture. So when a lecture in an online course is retrieved for a user, it may be very difficult for the user to understand this lecture without listening to the previous related lectures. It is also very difficult for the user to find background or relevant knowledges. So what we propose is that we let every slide in online course with plus their audio video as a spoken slide. And every spoken slide is labeled by a set of key terms extracted from the audio. For example, here are the spoken slides. They are labeled by these key terms. And then all the key terms are related by a graph, which we call Keynote graph. This is very similar to the knowledge graph, extensively studied in recent years. And here is an example of retrieving with an online course browser we developed in year 2009 on a course on speech processing I taught. And the query, here the query used is triphon. And this is the top 3 utterances retrieved. You can see that every utterance is listed and shown with the spoken slides they belong to. And these slides are labeled by the key terms and the title. So the user can decide whether he would like to listen to this slide or not. Suppose the user decides to select one of the slides to listen to, then he clicks it and he sees this. And here is a slide. And here says that you can play the whole slide or play the summary. And here are the key terms of the slides. If you don't understand the key term, well, here are the related key terms on the key term graph. Suppose the user found he didn't understand this key term of entropy. He can click here, and the machine says this. This key term first appears in these slides. You may go there to understand what that means. And this key term was then mentioned in these following slides. So this is a recommended learning path for the user to learn the key term. Okay, but now all these are just for a single course. How about we have a huge number of courses online? For example, a user may enter a key phrase. For example, machine learning to Coursera. Coursera says there are 750 matches. What can the user do? Well, we hope the machine can listen to all the online courses over the internet. And for example, here are the 3 courses on very similar topic. Then we hope machine can do this for the user. What this says is that this lecture of this course and this lecture of this course and this lecture of this course, they are talking about something very similar. And here is the sequential order for learning based on the prerequisite conditions. And this is something that's very similar to learning map. So below, I'll show you a very short demo showing how the machine can produce learning map from the online courses for the user. So we can click here to go to the system. This is a very small experimental system, including only about 40 online courses. We assume a student is interested in learning Python. So he types in Python here and go to search. And the system tells that there are 3 courses here on Python, each represented by a straight line. Every node here represents a segment of lecture. For example, we can click here to see the first lecture.
So now that we've understood our goal is to capture.
And this is the second lecture.
So let's get going.
And this second course and third course, we can click here to see the third course.
As part of the function,
link to get the learning map. Okay, this is a learning map because you can see that here, this lecture is where the 3 courses are talking about very similar content. And here are the order of learning or the learning map. Now, the next issue is we hope the machine can serve as the personalized teaching assistant. That means we have to rely on the question answering technologies developed in natural language area, in which the machines can answer questions from the user. Suppose this is a machine. For a given question, the machine gives the answer based on some knowledge sources, which is usually a set of documents retrieved from internet. Now, with spoken content retrieval, we can also have a set of spoken content serving as the knowledge source. So we have the text question answering as well as spoken question answering. So for text question answering, as we mentioned, based on a set of retrieved text document, machine tries to find answer for a given question. Now, for spoken question answering, this is very similar, except the knowledge source is spoken content. What we can do is use an ASR to transform this spoken content into a set of documents, just as this, and then feed these documents or the transcriptions into the question answering, for which, for a given question, an answer was given. Now, this is, of course, a cascading structure. As we mentioned, the cascading structure has a problem that ASR errors will propagate. So a better approach may be to try to do end-to-end question answering, such that it integrates ASR and question answering in one process. And for a question given by the user, the machine simply gives the answer. And this is the end-to-end. In this conference of Interspeech 2020, we have a paper presented here on how this can be done. Let me very briefly say the following. We propose a speech bird, which is learned audio and text jointly. It's very similar to BERT because it was first pre-trained by primarily random masks and then fine-tuned on the spoken content question answering. In this way, the machine can be end-to-end globally optimized for overall question answering performance. They are not limited by ASR errors because there's no ASR here. And the machine can extract semantics directly from speech, not from words via ASR. For more details, please go to the paper. Okay, this is the end of the second example. Let me give you some many remarks here. As we mentioned, Internet is the only largest archive for global human knowledge, and spoken language technologies offer a bridge to that knowledge. Of course, there's still a long way to go towards the personalized education environment we consider here. However, we did propose many small steps, and we hope these small steps may lead to the final destination someday, and someone may realize it at the right time in the future. On the other hand, we noted that machines are capable of handling huge quantity of data, so it makes sense to use machines in the way they are spatially capable and efficient, just as Google does. That is a spoken version of Google. Okay, this is the end of the second example. Okay, now let's talk about the third example, unsupervised ASR or phoneme recognition. This part of work is joint work with my young colleague, Hong-Yi Lee, who used to be my former PhD student. We all know that supervised ASR has been very successful, but it requires a huge quantity of annotated data, by which we mean every utterance in the training set needs to be annotated regarding what was said. And all these data are used to train supervised ASR. The problem is there are thousands of languages spoken all over the world, and most of them are low-resourced without enough annotated data. And this is why we are interested in unsupervised ASR, for which it can be trained without annotated data, by which we mean that the audio data does not have to be annotated, and the text data does not have to be related to the audio data. And these two sets of data are used to train unsupervised ASR. So the training data can be unlabeled, unpaired, which are easier to collect. This is something we could never do before year 2018. I need to first explain the use of generative adversarial networks, or GANE, which includes a generator and a discriminator. The generator can be an ASR system, which takes audio data as the input and assumes it can generate phony sequence as the output. The discriminator, on the other hand, takes the text data as the input. These texts are first transformed into phoneme sequences. Here we assume we know the pronunciation lexicon. And these phoneme sequences are real. So we have now two sets of phoneme sequences, the real ones from the text data and the generated ones from the ASR. And this one does have some errors. So we can take these two sets of generate and real data as the input to this discriminator, and the discriminator is trained to try to distinguish whether the input phoneme sequence is real or generated. When this discriminator is well trained, we retrain the generator. The goal is to try to fold the discriminator or to generate phoneme sequence more closer to the real phoneme sequences. When the generator is well trained, we retrain the discriminator again. In this way, these two machines are trained iteratively, and they improve themselves individually and iteratively. And this is GANE. Now we start with Model 1 proposed in year 2018. The audio data are represented as acoustic features, and they are first divided into acoustically similar segments of different lengths. Every segment represents a possible phoneme such as X1, X2, X3, and so on. We then transform every segment into a fixed length vector, which we call audio embedding. For example, X1 into Z1, X2 into Z2, and so on. Now, this audio embedding sequence for all the training data are then clustered into groups. Every group is given a number index, such as 2, 16, 25, and so on. In this way, the audio embedding sequence here can be transformed into a sequence of cluster indices. So we can have such as Z1 is number 2, and Z2 is number 16, and so on. And this cluster index sequence is taken as an input of a generator, which is simply a lookup table telling which cluster index should be mapped to which phoneme. For example, number 2 is silence, number 16 is this phoneme, and so on. In this way, the generator can produce a generated phoneme sequence. And this sequence is taken as an input to the discriminator, which also takes another whole set of real phoneme sequence from the text data of the training data, as we mentioned. In this way, the discriminator is to try to distinguish whether any input phoneme sequence is real or generated. And as we mentioned, this discriminator can be iteratively trained with generator. And generator in this way can improve the lookup table to have a better mapping from the cluster index to the phonemes. When the training was finished, we simply remove the discriminator here and take the phoneme sequence here as the output. And this is the phoneme recognition. And this is model 1. As we see, this is a clustering process followed by a GANE or a cascading process. Now let's look at model 2 proposed in year 2019. The audio data is also represented as acoustic features and segmented into segments of different lengths. Just as we did before, every segment is considered as a possible phoneme. Now the generator consists 2 parts. The first part is simply a phoneme classifier, or actually a DNN, which transforms every acoustic feature into a probability distribution over all possible phonemes. And the second part is a sampling process, which simply samples one such distribution over the phonemes for every segment. And this is the generator, which actually transforms the input audio data into a generated phoneme sequence. Now, this generated phoneme sequence are taken as input to a discriminator, which also takes other set of real phoneme sequence from the text data, as we just mentioned, which are real phoneme sequences represented in forms of one-hot vectors. Now the discriminator is trained to distinguish whether an input phoneme sequence is either real or generated. As we can see here, this gain is trained end-to-end. Even the DNN, or the phoneme classifier, is included in the generator, and it is trained in an unsupervised way. However, this gain is trained based on the initial segment or these phoneme boundaries, which may not be very good. In order to solve this problem, we can use another set of hidden models. In other words, we start with an initial segmentation or the phoneme boundaries and use these boundaries to train the gain. But the gain may not be very well trained because of the problem of the phoneme boundaries. But we can take the output of the gain, which are the phoneme sequences, as the pseudo label to train a set of hidden models. And this set of hidden models are used to resegment the training data to get better phoneme boundaries and use these boundaries for training the gain again. So this can be iterated. Okay, now we can see some results for models 1 and 2 on timid. And here are the phoneme error rate. We may know that label model 1 is very poor. The phoneme error rate is as high as 76, even for matched data, which means the text data and audio data are actually matched, except that they are not aligned. However, model 2 is much better, give much good results, and the 3 iterations with hidden models actually reduce the phoneme error rate to as low as 33. Even for unrelated data, that means the text data is very different and unrelated to the audio data. Why model 2 is better than model 1? We may say that model 1 cascading the clustering with a gain, while model 2 did everything end-to-end with gain, which is better. Now, you may say that 33 of phoneme error rate is really high. That's correct. However, if we look at this chart, which was taken from a paper in year 2011, which reports the milestones in phoneme recognition accuracy on timid, and which says in year 1989, the supervised trained hidden models gives a phoneme accuracy of 66%, which is almost the same as what we have here. In other words, unsupervised learning today is as good as supervised learning about 30 years ago. So you may ask, would it take another 30 years for unsupervised learning to achieve the performance of supervised learning today? We don't know. Now, we still have a Model 3 also developed in year 2019 based on a framework of cascading recognition and synthesis. We never knew how babies learn to speak from parents, but we may assume something like this. The parents said daddy, and the baby learns to say daddy by minimizing the reconstruction error between the two, or by listening and reproducing. The baby may learn some basic sound unit somewhere here. Of course, for a different utterance, daddy, this sound unit may be different, but can be clustered some way and represent as vectors here. So for any input vector, input utterance here, we may assume the first part is somewhere here, so it is T. The next part is somewhere here, so it is at. And then the next part is somewhere here, so it is B. So this is tap, or this is phoneme recognition. In this way, the training data needed will be audio data only without text, just as the baby learns to speak without text. However, we'll need a small set of pair data because we need to tell the machine which unit corresponds to which phoneme. In order to implement this concept, we propose a autoencoder plus quantization. As here, the input signal are first encoded into a sequence of vectors, and these vectors on frame level are quantized into a smaller number of phoneme representations, and these representations were taken as the input for the decoder to synthesize the original signal. So this is encoder and decoder, or ASR and TTS. Now the core part is the central part of quantizer, so let's take a closer look at it. The quantizer includes a learnable codebook with finite number of code words. So for every input vector, we try to find a code word with minimum distance, and then represent this input vector by this code word. For example, code word number 4 or E4. Now assume the next several vectors are also close to E4, so represented by E4. Assume the next vector is different and closer to E2, so represented by E2, and so on. In this way, the input vector sequence is represented as a sequence of code words of finite size based on minimum distance and clustering, considering the acoustic properties. And that's why we can call it the process of phonetic clustering. Next, we assume that a sequence of the same code word can be represented by a single code word. So a sequence of E2 represented by a single E2, and so on. So this is the temporal segmentation. Now with this, the code word here are actually phoneme representation sequence. So this is the quantization. Now the problem here is we don't know which code word corresponds to which phoneme. So we need to have a small set of pair data to train machine to know this. This can be done by first assign one phoneme to each code word, and then we assume a probability for every vector belonging to a phoneme or a code word. With that, we can match with the pair data by maximizing the probability or minimizing the distance. In this way, the quantization can be accomplished. So we put this quantization back to the original framework, and it is this. It can be trained end-to-end with audio data plus a small set of pair data without text. When the training is finished, we can remove the decoder at the end, because the phoneme sequence here is the phoneme sequence output, and it is phoneme recognition. Now the initial results were obtained on LJ speech for a single speaker only, in which we used 22 hours of audio data plus 20 minutes of pair data. The phone error rate we received is about 25%. We may reduce the size of this pair data, but the phone error rate will be increased. Recently, in year 2020, we saw more related work reported in this area. However, they are beyond what I can say today. Okay, this is the end of the third example. Let me say some mini remarks. Deep learning really makes tests impossible before realizable today. There are certainly much more crazy concepts yet to be explored. More technically, I would say unpaired data may be more useful than we thought. And end-to-end training is more attractive than cascading in the context of deep learning, because overall performance can be optimized globally as compared to locally. So this is the end of the talk. This last page. Let me give you some concluding remarks. I would say doing something we never could is interesting and exciting. Although challenging, the difficulties may be reduced by the fast advancing technologies, including deep learning. 15 years ago, we never knew what kind of technologies we could have today. Similarly, today we never know what kind of technology we may have 15 years from now. So anything in our mind could be possible. Also, I like to say this may be the golden age we never had for research, because we are having very deep learning, very big data, very powerful machines, and very strong industry, which we never had before. And therefore, it's possible to do something we never could. So this is the end of the talk. Thank you very much for your attention.
Thank you very much, Professor Lee, for a very inspiring talk. So let's see, we don't have that much time. We have actually about 3 minutes before the hour is up. So please seize the opportunity to ask questions. Now, I already see some questions being placed in the chat room. The first one actually comes from our ISCA president, John. His question is, on the child speech topic, how would you think the phone selection and error may be impacted in text, which is formally written, versus spontaneous conversational speech? Children have more difficult time with some phonemes versus others.
Oh, sure, certainly. It would be very difficult to have the children's voice to be recognized, and we have to, I think that is still a lot of work to do. And what we mentioned here is just some initial thoughts about how this can be started. And for more work, we need to think about much more about the details.
Yeah. Thank you, Professor Lee. And also, I wish to say, John, also, thank you for a very nice keynote talk. I see another one in the Q&A. Thank you for an amazing presentation. And here is my question. For the unsupervised ASR used GAN method, I am wondering if the input of the generator was coupled or set aligned with the input of the discriminator during the training stage. So this is relating to your earlier slide on the GAN and ASR.
Yes, I think the detail is in our papers in Interspeech 2018 and 19. But in general, the generator and discriminator are trained using the same set of data. For the Model 1, the training data includes audio and text. They are related. They are actually matched, however, not aligned. In Model 2, we use completely different, unrelated data for audio and text. So they are different and unrelated. So the two models are trained in different conditions. However, in the slide I mentioned for the phony error rate, we actually try to use the same set of unrelated data to test both models, and that's why we can compare the two models. But for more details, you can see our papers in Interspeech 2018 and 19.
Thank you, Professor Lee. One more question. I know I'm eating into the coffee break now, but one more question from Seren Walbridge. Thank you for the very interesting talk. This question is about the personalized education environment example that you have discussed. How is the order of learning determined? That is the order of topics in the graph. Is it personalized? And if so, how is it personalized?
Right now, it's not personalized, but primarily based on the semantics. For example, the semantics of the keywords, semantics of the topics, and so on. for example, we actually use the word net to know which word covers which other words and so on. And of course, that gives it some sequence and so on. So for detail, you can see the actually on my slides, I always have a paper list on the right lower corner, and that part was in our Interspeech 2015 paper in Dresden. So detail is there, you can find there.
Okay, thank you very much again, Professor Lee. And thank you everyone for attending the keynote. It's very well attended. I must say that Professor Lee's slides will be shared. I think the video also, we will be sharing the contents on the Interspeech official website. So you may refer to the website if you want to ask further questions. The website has a Q&A zone. So please feel free to go back to the official website and type in any further questions. We're short of time on questions, but the good thing about being online is you can always type in questions later on. So with that, thank you again, Professor Lee. Thank you, everyone.
Thank you very much.
So we have a shortened coffee break now, and the sessions will start at 7:15. So thank you, everyone.